Okay, so my name's Greg Nolan. I'm an architect by profession, and it's always a bit hard following one of Christoph's talks because everyone is so inspired to go out and make snake-shaped, complex glulam structures, thinking you can get them on the most every street corner. It's difficult because what I'm trying to do, I'll be looking to describe to you now as a new WoodSolutions guide, which in some ways can be compared to a cookbook. In that I've been involved with timber design and education now for quite a long time. And one thing I think is what most of us will admit is that in a lot of the university education, both for architects and engineers, is that we don't get a lot of wood background in it. And so for many of us, we're trying to catch up with a whole range of things and look at presentations like Christoph's with awe about how the hell do we get to understand some of this stuff when we weren't actually taught it at university and we don't actually have a framework in which to set it. So in part, one of the reasons for this guide is to start to establish some of those frameworks and to start to provide some of that background information so that people can improve their design with wood and progress in their practice. Okay, so the authors for the guide is myself and engineer Dan Tingley. Now Dan is an engineer who practices across both Australia and North America. He's a professional of probably 50 years experience in working with wood and timber structures. And we worked cooperatively on the guide in that I helped establish the systems that we'll try and describe through. And Dan and his teams then provided engineering commentary, worked on case studies, etc., as you'll see. So the aim of the guide is then to assist practicing structural engineers and other building design professionals to confidently develop conceptual structural designs for timber-rich buildings and structures. So it has been conceived really as a guide for engineers to get you from a stage where you're not quite sure about the options with wood to having greater confidence that there's certain things you can do. So that's one side. The second side is then for the architects in the room to understand what this shows is possible, to take it along to the engineer and say, see, we can do it, so that you get over that barrier of neither side actually believing what is possible. So the approach we take is we take a whole of process approach in that it explores then the available structural systems, connections and material options, design approaches, performance requirements and material properties, and it includes something but quite important here includes regular options for systems and materials. Now, regular, we decided that regular was probably the best word, is that we didn't want to put in, we're not trying to be encyclopedic. We're not trying to cover everything that could possibly be available or every minor permutation of the thing. It was things we wanted to cover enough things so that most people could get most of the options most of the time. And that's where we drew the boundary. We didn't try and extend it into quite much more complex structures, but things that would cover maybe 90-95% of jobs that most people would come across. We also then included 2 worked examples, because for those in the engineering fraternity, you need to have greater we wanted to build confidence in that people could actually calculate the various components and could see how they were calculated. So the guide's broken up into a range of sections, and the sections then are aligned with the stages of the conceptual design process. So you start off with brief formulation, you work then through to the information search, all the things that you need to understand as you seek to develop a solution. There's then conceptual design stages, and then there's detailed design and documentation are recognised. Now, the guide doesn't want to go into detailed design. It doesn't want to provide you a fire detail. It doesn't want to show you how to design for durability, but it wants to direct you to the other guides that exist that will do that. And so this then becomes a directory so that you know that at this stage you should go off and get that guide and look at that in more detail. So I just want to address then what we handle in each guide. Now, the other key thing is that we've used icons a lot, and I'll show you what that means in a minute. So if we look at the sections, section 1 deals with why would we want to use wood in the first place. So there's a range of environmental and cost and other implications that come when you decide to use wood, and we need to get those out at the beginning. The next is what is our systems options. So if we're looking at a system of assembly, by either structurally or architecturally, or preferably both, what then can we choose from? The next one then is that if we've got these systems, how we join them is going to affect both the cost and the aesthetics of the combinations in the design. So we look at the connection options. We then have to make the thing out of materials. So then we look at the material types that are available. We then look at the construction options, how you're going to put this thing together. We look at then design approaches. So there are certain ways in which things have to be assembled to satisfy particular sets of performance requirements. Now, I'm going to go through each of these sections again in a couple of worked examples in a minute. So this is why I'm rushing through these now. The next thing is that there's actually a lot of stuff about wood that most people don't realise. A key thing is that if you're used to using steel and concrete, then you're used to making man-made materials that generally have a high energy, a relatively limited product range, and they're being designed to satisfy to give you a particular performance level. Now, unfortunately, wood's different, because with wood, the tree grows what it wants based on its genetics, and we try to harness that genetic output to do different things, which means we've got products that are highly variable. They're highly variable, they're hygroscopic, they're anisotropic. Now, if you come from a steel and concrete background and you don't actually know anything about those things, then there's lots of problems you're going to face. So we had to explain them somewhere, and that's where we explain it. So if you want to know why wood shrinks and why moisture content is important, and because Christoph will have mentioned moisture content through his presentation and how people had to cover things up and how it causes all these problems, well, we cover why that's a case there in that material properties section. I'm not going to deal with that much else today, except to say that it's there. Beyond material basics, there is then material properties. Now, properties is different to basics because in the first one we explain what moisture content is, how shrinkage is related to moisture content, etc. in principle. With material properties, we then go, well, if you've got this species, this is the shrinkage rate you're likely to expect. So if you understand that, make the difference between those two things. We then deal with performance requirements, and there are a couple of specific performance requirements which deal with wood, which are different to things that might apply with other material bases. So they're set out, and we look at two things. One is basically the National Construction Code, which of course we all read and move around with us. And the second one is that there is a whole range of things that are tied up with the fit for purpose requirements in the Australian consumer law, which with wood we've got to make sure we handle some of those things because it's a variable material again, and it might do some things that we don't expect, we wouldn't normally expect if we're using a steel and concrete option. There's then a section on aspects of using AS 1720, and then there's two worked examples. This is the little 3Ds for each of them, and we'll have a look at what's included in each of those towards the end of the presentation. Okay, and then we reference other WoodSolutions guides, and these are two that people will be using quite a lot. One is the timber frame construction for multi-residential buildings, class 2 and 3, and the other one then is the timber service life design guide. And if you're using wood outside, then that should be something that you've got readily available to refer to on almost every occasion. Okay, so designing with a natural resource is different than designing with a man-made one. There's a whole range of reasons for that. Is that the wood is generally processed quite near to where the wood is grown, so it's a regional based thing. Wood production is not that capital intensive compared to something like steel production, and it's highly workable, and you get a whole range of different products out of it. So to help balance and understand some of these variabilities, or to at least for us to describe them regularly, is we use a lot of icons throughout the text, because we didn't want to try and put all the information in one spot, because you just can't explain it all. So generally we're using icons for materials. So obviously these first four are particular materials you might get at a hardware store, and assemblies. So the four on the right, the right, are ones that you could assemble up from some of these other materials. We also then use icons for construction options, how you might fit one thing next to another, how you might run a bracing system, or how you might approach something like prefabrication. So given that overview, what I'd like to do now is we want to just generate a conceptual design for a timber-rich structure based upon the various sections. And so if we're going to do a conceptual design, there's a range of things we're going to do. We're going to try and work things iteratively. We're going to select a number of options for each category of structural element that we've got to put into the design. We've got to establish a base of assessing these different potential options. We've got to determine load paths. We want to get some basic initial sizing to see exactly how the thing might go together. So things that we've got to consider are sort of what type of building we've got, and therefore what sort of structure does that lend to the solution. What are our options for our structural components? What are the options for putting them together? What materials should we use? What are the options for assembling the components into a building? Because there's lots of different ways of doing that. And wood is highly workable, so it's very, very easy to get precise construction with wood if you want to. And then there's approaches to satisfying the building and components performance requirements. So if we take each of those steps in sequence, and most of you will have noticed that a lot of our sections actually align with each of those particular bits. So if we look at the type of building, then if we're looking at building typologies, we've probably got three main ones. And we might actually use these in combination. So first is we'll have some sort of closed frame where we've got regular walls, relatively short spans, and this might be very common in class 2, 3 and 4 type buildings, where we've got walls between apartments, between hotel units. The next is we'll have an open frame system, whereby we're looking for larger spans that we want to be able to change around at particular times or have as big open areas. I mean, this building here is an open frame structure. Then we might have a single level system where we've got maybe stuff on the ground in a single story, or where this might also then apply to the roof of an open frame structure, or even the roof of a closed frame, because obviously the roof has different performance requirements to the intermediate floors. So in our little example, we're going to pick an open frame system. So what are the structural options we've got then? Structural systems options we've got. So really there's probably three major components that we want to be able to put together. We want to put together a spanning system, that's either a floor or a roof. We've got a support system such as columns or walls that might then support the vertical loads. And we've got a lateral resistance systems which are going to help us resist the horizontal loads such as wind loads and earthquake, where we've got to take those loads and get them down to the ground through the vertical systems. And we want to combine these up. So I'd like to credit Mr. Alexander Calder for his little drawing there of structures. Okay, so if we're looking now in the guide, we try to address each of those different systems. And so if we're looking now at a spanning system for floors. So here we've got three options for floors. The first is we can have a floor or joist deck, and the joist can be over the top of the beams or running into the side of the beams, so they're options. We've got massive timber as a floor system. We've also then got concrete and timber composites. So we can make a floor system then where we've got timber and wood working together, and that's providing us a system for the option. We're providing with each of those then basic span ranges for things like the joist or for panels or for the concrete and timber. Now again, remember, always come back, we're dealing with regular options here. We could probably go further, but we're not trying to do gymnastics with this too much. And then we're giving common span to depth ratios for systems that you may use in these cases. Now, if we take massive timber as our example in our project, is that we would then go to the detail then in the guide of massive timber option. So here's our massive timber drawing here on the left, and across the top we then have regular beam options, because obviously if we've got a CLT panel, we've got to put it on a beam. The beam's going to be on a column, so the beam we're regarding as part of the spanning system, and there's various things that we can use then as our beam. Each of the icons then ties up with something we'll describe later on, because we need to describe what glulam is, and that comes later. So if we've got our regular panel options there, we've got a range of things we can do. We can use CLT, we can use GLP, which is a glue laminated panel. So we're not cross-laminating, we're just face laminating. We've got an NLT, which is a nail laminated timber. We've got an LVL, which if we've got it thick enough and our spans aren't large, aren't too big, we can actually use those as the panels. Or we have a stress laminated panel, which from the notes you can see are generally used for things like bridge decks. They're not commonly used in buildings, but they are an option. So if we say we're going to have a CLT system for our floor panels, or we want to investigate a CLT option, we will then move to see what our indicative spans are if we're using a CLT floor panel. So we have a series of guidance tables in there for material of particular size, and then in particular application, to give you guidance as to about how far that stuff will span. So if we look at this in a bit more detail, is that if we say we're going to have a 200mm CLT panel, or that we want to go somewhere between 4 or 5 metres, or maybe about 5 metres, we've got a multi-res option. Sorry, in our case we've got an office. We want to go a simple 5 metre span, something of that order. Then we're going to know we're going to need a CLT panel of about 200mm. Now, of course, this isn't optimised, but again, we're not into detailed design, we're only into conceptual design at this stage. So this is then providing us enough information to give a reasonable estimate of how much we're going to need to go a particular distance. Now, the diagrams, the span tables are particularly fuzzy. Well, they're not fuzzy, but they're particularly unclear, and because we didn't want to have anything up there where someone was scaling it off and says, oh, it's actually 5.2. Therefore, we'll actually use that as our basis. It's there to give you a feel so that later on you then in detailed design you can come through and work out exactly what the sizes are. If we're looking then at roof systems, there's a whole range of different roof systems that are available, and we can characterise those. So we have, which is sort of beams and purlins, beams and rafters, which is a slightly different arrangement. We've got light nail plate trusses, heavy trusses, tied frames, portal frames, arches and domes. The end two are probably much rarer than the ones at this end. And if we can say in our job, we're going to look at this one. We're going to take the simplest one, which is beams and purlins. We're going to have a primary beam. We're going to run purlins straight across. Now, if we look at that one then in a bit more detail in the guide, then there's a range of options that opens up for us. If we want regular beams, there's actually a range of different ways in which we can have a regular beam. A beam doesn't have to be straight. A beam can be curved, it can be tapered, it can be on an angle, etc. So all of those top drawings are actually your standard operational drawings for what a beam might be between columns. Coming down from that, we've got the materials then that are regular options that you could use depending on whether you're spanning greater or less than 5 metres. Now obviously the ones that are greater than 5 metres can come back to less than 5 metres, but if you're going over 5 metres, they're the sorts of things you're going to need. And there's also then the purlin options with some notes then about span to depth ratios and nominal sizing. So once you get over about 4.8 metres, you start to get into some problems in what materials you can use. So we then provide span tables then for things like indicative rafter spans, and we use a couple of standard spacings, an 18-degree pitch, and then we use a range of different materials to give you a guidance as to if you've got this material of this size in this wind classification, it's likely to go about that far. So the grey bar is single span, the extension into the green bar is then if you've got a continuous span. So the aim of this obviously is then so that if you're doing a preliminary design, you can actually go through the guide and say, okay, I'm likely to need something of this size if I'm going to have these sorts of things at this sort of spacing. So in our case, we might say we're going to use LVL, we've got a 240 by 45. So if we've only got single span, we're likely to be able to go out to about 4.2 metres. If we've got it as a continuous span, we might be able to take it out towards 6. We then need support systems for our floors and our floor systems and the beams. And in this case, we might look at a massive timber one. And therefore, there's a range of massive timber options that we can use in a wall system. We can use CLT, we can use glulam, we can use LVL, we can use nail laminated timber. Each one will have particular properties, particular aesthetics, and particular economics. You can also see at the bottom there is we've got regular construction and prefabrication options. So obviously, if you pick a particular system like CLT or LVL and you've got a massive timber system, then it leaves it open for you to prefabricate the building in a different way than if you've picked something like a stud wall frame or a stick build. So certain things lend themselves to prefabrication more than others. So we're noting there at the bottom the prefabrication and construction options that become available, and they're again explained in a bit more detail later on. So if we go with CLT, in these particular case, we can then come to our lateral restraint systems, and we've got a range of options for this. And if we say we want wall, we're going to use wall diaphragms in our particular case, then we've got particular wall diaphragm options, and we know we've got CLT panels already, so that is likely to provide both some of our support systems and then some of our lateral restraints. Though if we've got a stud frame wall system, we know we can see there that we can sheet it in a whole range of different materials that will enable us to get particular load capacity into those wall systems. We don't go down to the detail where we can say you're getting this load capacity. We're going to say here are your options. You then can develop it up further to work out what loads you've got to resist and the different materials and fixings, etc. you need to do that. So there are various ways then you can join bits of wood together, and how you join them is going to impact your aesthetics in your structure. There's really basically three major types of junctions, of connection systems. One is you can have a connection where you've got timber on timber. That's up. The next is you've got timber that's joined with fasteners. And the next is you've got one where you've got timber, you've got a connector, and then you've got fasteners. So you're shedding load from the wood into a connector, through the fasteners, and then back into the wood again through the fasteners. So we look at the various types of connections you can actually have from an architectural or an assembly point of view, and look at how they operate, whether they're a timber to timber, whether they're a timber to fastener, or whether they're timber connectors to fasteners. Now, if you take simple contact transfer where you've got, say, a bearer and a joist, then obviously the primary load transfer is from the joist straight onto the bearer. So it's timber to timber contact. But obviously we don't just put the timber there and then walk away and hope and don't do anything else. We nail it down, we strap it up, we do a whole range of other things. So we're getting secondary load transfer by different means. If we skew nail it, we've got a timber to connector system, timber to fastener system, and we're using that to locate it. We may also strap it, and so we're using the strap as a connector. So where we say we've got primary load transfers through the black box, the other one is through the secondaries. So if we look at fasteners, we include some illustration on the fasteners, the type of fasteners that are available, and some of the primary considerations when you're dealing with fastener connections. So this diagram here on the left-hand side is the spacing requirement diagram for bolts out of AS 1720. So it provides you some basic guidance early about how far apart the bolts have got to be. Now, it's my engineering colleagues, and part of the reason we've put quite a lot of detail into this connection bit is that my engineering colleagues tell me with great conviction is that with most timber structures, actually God is in the details. God is in these connections, is that the connector can actually be the thing that determines the size of the element rather than simple things like bending or strength. So we have obviously then considered exactly how these connectors may go together. So then we look at regular connector types. So connector is the thing you're going to use, that you may use then to join two pieces. So whether you're using a wood gusset or a metal gusset or a nail plate, all of these are different connector types that we use to enhance connection of bits of wood together. And then we look at connector types and what they would look like. And obviously, here's a man here in our photograph here on the left. He's obviously an advocate for BIM, so he can know exactly where then to put the nails. But obviously, he's putting together a timber fastener connection. There's bits of wood that got to be joined, and he's using lots of fasteners then to do it. And these diagrams then show you various ways in which timber and fasteners can be used. The fasteners could be a dowel of varying sizes. So a dowel could be a bolt, a dowel could be a dowel of maybe 5 or 6 millimetres or 8 millimetres, or a dowel could be a nail, which is effectively what our man's putting in. But the thing you'll notice when you've got a timber fastener connection is that one piece of wood's got to go past the other. So you can't arrange them in plane. And that's then a consideration in how your aesthetics are going to work, because you can't just get a nice smooth edge, you've got to start running things past each other. if you want things to be in the same plane, there are other options, and things like fin plates are options then that allow you to connect things in plane. So obviously if we've got, I don't know, does an arrow come up? There we go. So obviously if we've got this connection at in the column to the ground or the one above, we obviously then have quite a neat in-plane connection with a steel plate or a plate concealed inside the element, and we're using then the fasteners, be they dowels or others, to then connect take the load from the wood into the connector, across to the other side, and then back into the wood again. And of course you can see one of these really nice ones here on the left, where you've got some of the new series of screw-in fixings that a lot of the major screw manufacturers are starting to make now and supply to service the renaissance in wood that we've got happening. So obviously the aesthetics of this is different than the aesthetics of running something past each other. And with aesthetics comes cost implications. So we do actually have a table in the guide, which is too detailed to actually put on a slide because you wouldn't be able to read it anyway, that does give you some guidance as into, with these different types of arrangements, can pieces go past each other, how easy or hard are they to fire rate, and how relatively expensive they are on a reasonably cheap, middle of the road or really expensive scale on a $1 mark to a $4 mark scale of likely expense. Now, one thing, if you get the questionnaire on this presentation, one of the answers is the guide does not cover detailed comparative costings, because detailed comparative costings are far too hard. There's far too much moving all the time to be able to do that. So there's one answer for you. Okay, so materials have to then be available to make the components, and we look at three major types. One is a generic component. I think Paul made a comment earlier about commodity products, and really this generic is a commodity product. It's something you can buy at the hardware store. The next is you make a fabricated component, and a nail plate truss is a fabricated component. It's made for a location in a job and comes to site. The other is site assembled things, which are things that you can't actually make somewhere else. You've got to actually put bits together on site. And if we then look at each of the material options, be they rounds, sawn timber, or assembled elements from sawn timber, veneered-based products such as plywood or LVLs. And in our little building program, we were looking at sawn timber and CLT, both of which are made from sawn material. We've got strand-based products, combined elements where we've got one lot of wood type going with another lot of wood type, and composite elements where we've got things like there at the bottom where we've got timber, maybe sawn timber. We've then got a sheet material which might be plywood or OSB or particle board even, and we're then putting concrete on the top of it. So we've got a range of different materials going in at the same time. If we look at something like sawn timber, there's then tables to show you the sizes that are readily available, and if we're making a reasonable building, we're going to be using machined seasoned material. It'll have a range of sizes that are available. It'll have a range of grades, which we describe. Those grades will be defined by standards, which are described, and there'll generally be some guidance as to supply. We have attempted, wherever possible, to get basic structural characteristics for each of these materials in. So we actually do have, from one or two of the LVL producers, some of their basic performance characteristics of their products, and we've sort of amalgamated them together to give you guidance. Some of the products, though, are almost impossible, so it's almost impossible to get what bending and stiffness is for some of the OSB products that are brought in Australia. So we obviously haven't included them, but we would have liked to. Okay, so there's options then for how you build. And we've set up 3 different types of building options. One is we're calling it prefabricated intensive building. That is where we're trying to prefabricate as much as possible off-site, bring it to site and crane it in. So that's one option. The next is one I think is sort of not discussed much, but which is a highly useful one with wood, which is site-based component assembly. That is where you take components that are relatively small, you bring them to near the site, you assemble them into a bigger bit that you can't put on a truck, and then you pick them up and you put them in the building. So the photograph that's there is actually the roof of the National Portrait Gallery in Canberra. So each of those components that you see on the crane there is about 14 metres long. So they actually brought all the trusses from the truss plant as flat pack. They then assembled them next to the building site into these modules and picked the modules up and put them in place. And it saved them a heap because they could do a lot of things on the ground without having to pay for scaffolding and a whole range of other things. Now with wood that's quite easy because the wood comes at the right size, it's relatively light and it's relatively easy to handle. The last one is then general construction, which is, most of us are used to, which is you make it up and you just handle everything, cut everything to size. So if we're going with prefabricated intensive building, there's various things we can do. We know we can make volumetric modules, we know we can make panels, and we know we can make a stick, and we can cut the stick to the right size. We might even put connectors and other things into it. And in our building, we could say, okay, well, we're going to panelise the floor, we're going to make sticks, and then all our beams and columns are going to come, they're all going to be the right size, and all the connections are going to be prepared before we actually get it there. So from there, if we want to approach the buildings and components performance requirements, there's a range of things we've got to start to look at, because obviously the structure is just one, and it may be that the structure isn't structural loads may not be the thing that actually determines exactly what the size is. It might be things like acoustic performance or thermal performance or fire performance, all of which are going to come into how we design the various components. So we cite what each of those are, and then we indicate the major methods by which you would then resolve those things. So if we're looking at fire resistance, we've obviously got 2 major approaches. One is we can cover it with board, we can encapsulate it in some way. The other is that we can then do a charring factor, sacrificial sizing, to mean that we can show the wood, and with a fire we know it's going to char at a particular rate, and we might say that in our design we're going to actually start to take that approach rather than the other one. So if we look then at the conceptual things that we've covered the type of building, we've looked at the options for the construction system, we looked at the options for connecting the components, the materials that are available, the options for assembling it, and approaches to satisfy the buildings and components performance requirements. So if you just look at this little photograph here, that's a little job going up in Tasmania with one of the fabricators we've got there who's pretty inventive. And with this job, we've got obviously a single story project. Our major components are light nail plate trusses. They've been conceived as a site assembled prefabricated job. So all the trusses came to site, everything was assembled on the slab, on the ground, and then the roof was put into place. And on this job, quite a little job, it saved the builder about 70 grand. Right, by working through this process and coming up with that as a solution compared to what they'd originally priced. So each of these options then obviously we've got in the guide, and this is an output that could arise from it. So if we look then at worked examples, we've got 2 worked examples in the guide. One 7-storey mixed use, and the other's 10-storey. So if we look at the 7-storey one, we tried to get the case studies to show different things. Is that this one we've got floor to floor, ground floor we've got 4.5 metres, upper levels effectively you've got a 3 metre floor to floor height. With this first option, most of the floor are made of joists, and the joists are all nail plate trusses, and they've then got a fire resisting system underneath them. There's a dome on the top, and there's a portal frame end on the building also. So the grid spacings change. There's a transfer beam there in the middle of on the ground floor, and each of these things is then shown through in detail. With the second one, there's a 10-storey option with a pool on the 9th floor, just to add a little bit of interest. So this is conceptualising something where you've got a gym or something on the top floor, and you want to include a pool on that top floor. So here's the basic characteristics of the option. Effectively, everything's at about a 5.8 metre grid spacing, where you've got beam systems and you've got a secondary beam that's splitting the 5.8 into two minor spans to keep a thin CLT floor system. Ground floor is concrete, and then you've got the wood above. You've got effectively a glulam option with CLT systems, and this pool in the middle. So what the case study does then is it identifies each of the elements that are in the building, such as these ones here on a level 9 floor beam supporting the pool, or a normal roof beam, and then works through the detailed calculation of that element, given an assumed size at the beginning, does all the checks, etc. of that. Okay, so in summary, the guide aims then to provide practising structural engineers and others some greater confidence in developing timber-rich solutions for buildings and structures by hopefully taking away a whole lot of the unknowns about how can I actually get this thing to connect up to that other thing, and what sort of products do I have, and what sort of standards are governing the manufacture and performance of those products. And then to provide a whole of process approach to the selection of the structural systems, particularly for regular options. So obviously we won't have the details of the swatch building in there, or the componentry that you might use in such a structure, but you should be able to get details for a number of regular timber-rich options up to about 6 to 8 stories out of some of the guidance that the guide provides.